Every map of the solar system you have ever seen is wrong. Not approximately wrong, not drawn at an inconvenient scale, structurally, fundamentally wrong in a way that removes 99% of the actual territory. The diagrams in textbooks show the sun at the center, the 8 planets arranged outward in a flat disk, and then either a blank margin or the label deep space where the image ends. That edge of the page, wherever it falls, is almost always placed somewhere near Neptune, roughly 30 astronomical units from the sun. But the sun's gravitational territory does not end at Neptune. It does not end anywhere near Neptune. The actual gravitational reach of our star extends tens of thousands of times further, encompassing a volume of space so immense that Neptune, from that perspective, is not at the edge, it is in the center. Everything the textbook calls the solar system is a tiny, densely packed cluster of rocks and gas at the heart of a structure that dwarfs it in every dimension. That outer structure is called the Oort Cloud, and understanding what it actually is, where it came from, why we have never photographed it, and what it means for any future attempt to leave our star system, changes the way the solar system looks entirely. Start with scale, because the scale is where the picture first breaks. 1 astronomical unit is the average distance between Earth and the Sun, approximately 149 million kilometers, or about 93 million miles. It is a large number, but it is manageable. Light takes about 8 minutes and 20 seconds to travel that distance. Neptune sits at roughly 30 astronomical units. From Earth's perspective, Neptune is far a spacecraft traveling at the speed of New Horizons, which crossed Neptune's orbit in 2015 after 9.5 years of flight, gives some intuition for how far. But 30 astronomical units is still a distance that can be crossed within a human lifetime by robotic spacecraft. The Oort Cloud does not begin at 30 astronomical units. Current estimates place its inner boundary somewhere between 2,000 and 5,000 astronomical units from the Sun. That means the inner edge of the Oort Cloud is at minimum 67 times further from the Sun than Neptune. At maximum, it is 167 times further. And that is just the beginning. The outer boundary of the Oort Cloud extends, depending on which estimates you use, to between 50,000 and 100,000 astronomical units. At the far end of that range, the cloud reaches nearly halfway to Proxima Centauri, the nearest known star to our Sun, at approximately 268,000 astronomical units away. The solar system, properly measured to its gravitational edge, is almost half the distance to the nearest neighboring star. To make these numbers viscerally real, rather than just numerically large, try a scale model. Set the distance from Earth to the Sun as 1 centimeter, a distance you could traverse with the width of your thumbnail. At that scale, Neptune sits about 30 centimeters away, the distance from your thumbnail to the end of your arm, roughly, still in the same room, still reachable at that same scale. The inner edge of the Oort Cloud begins somewhere between 20 meters and 50 meters away. You have walked out of the building. The outer edge of the cloud stretches to between 500 meters and 1 kilometer from your starting point. You are now in a different neighborhood. The entire planetary solar system, every planet, every moon, every ring, Every asteroid between Mercury and Neptune is contained within the area of your thumbnail at the center of a sphere, roughly 2 kilometers in diameter. That sphere, that 2-kilometer wide bubble in the scale model, is the actual solar system. The planets are the thumbnail at its center. The shape of the Oort cloud is the next thing that surprises people, because it does not match the shape of the solar system they are used to seeing. The planets orbit the Sun on nearly the same flat plane, a disk, the result of the solar system's formation from a rotating cloud of gas and dust which flattened as it spun. The asteroid belt, the Kuiper Belt, just beyond Neptune. Even the scattered disk of debris outside the Kuiper Belt all share this rough planarity. The solar system, as we typically picture it, is fundamentally flat. The Oort cloud is not flat. It is a sphere. It surrounds the Sun from every direction above the plane of the planets, below it, to all sides. It is more accurate to think of it as a shell, a hollow globe of frozen debris encasing the entire planetary system at an enormous remove. The Sun, the 8 planets, and everything in between, including Voyager 1 itself. The farthest human-made object sits deep inside this shell like a grain of sand at the center of a basketball. The Oort cloud is itself divided into 2 regions with distinct properties. The inner portion, sometimes called the Hills cloud after the astronomer Jack Hills, who characterized it in 1981, occupies the space between roughly 2,000 and 20,000 astronomical units. Despite being called the inner Oort cloud, it is structured differently from the outer region. Rather than being a perfect sphere, the Hills cloud is shaped more like a thick disk or torus, an oblate structure that retains some memory of the flat disk from which it formed. It is also considerably denser than the outer region, contains an estimated several times more mass, and a much higher concentration of objects per unit volume. The outer Oort cloud extends from roughly 20,000 to 100,000 astronomical units and is the genuinely spherical component. Objects here are distributed uniformly in all directions, with no preference for the plane of the planets. This is the reservoir that supplies the long-period comets that drop into the inner solar system from apparently random directions. And it is what Jan Oort analyzed mathematically in 1950 when he proposed the cloud's existence. The material in the Oort cloud is not the familiar rock and metal of the inner solar system asteroids. It is primarily frozen volatiles, water ice, carbon monoxide ice, carbon dioxide ice, methane, ammonia, and various organic compounds, all frozen solid in the deep cold of the outer solar system. These objects are ice bodies, the same kind of material that makes up comets when they fall toward the Sun and begin to sublimate, releasing gas and dust that form the distinctive coma and tail. What makes the Oort cloud objects especially significant to planetary scientists is their age. These frozen bodies have been sitting in the deep freeze of the outer solar system for approximately 4.5 billion years, essentially since the solar system formed. The temperature in the outer Oort cloud is only a few degrees above absolute zero, minus 270 degrees Celsius or so, barely distinguishable from the background temperature of the cosmic microwave background. At those temperatures, chemical reactions are essentially frozen out. The material is preserved in a state very close to its original composition when the solar system was young. This makes long-period comets that fall into the inner solar system scientifically invaluable. When a comet from the Oort Cloud approaches the Sun for the first time, the heat begins to sublimate its outer layers, releasing material that has been locked in cold storage since before Earth existed. By analyzing the chemical composition of a comet's coma and tail, scientists can study the chemistry of the early solar nebula, the cloud of gas and dust from which the Sun and planets formed, in a way that no other sample can provide. The European Space Agency's Rosetta mission, which arrived at Comet 67P/Churyumov-Gerasimenko in 2014 and deployed the Philae lander onto its surface in November of that year, performed the most detailed analysis of a comet ever achieved. While that particular comet is a short-period comet originating from the Jupiter family rather than the Oort Cloud, the techniques developed demonstrated the extraordinary complexity of cometary chemistry, detecting glycine, a simple amino acid, along with phosphorus and a suite of organic compounds. Oort Cloud comets, being even more pristine, may carry even older chemical signatures. The question of where all this material came from, how trillions of icy bodies came to occupy a shell extending halfway to the nearest star, requires going back 4.5 billion years to the formation of the solar system itself. The early solar system was a chaotic environment. The Sun had recently ignited at the center of a collapsing molecular cloud, and the remaining gas and dust settled into a rotating protoplanetary disk around it. Within this disk, solid particles began to stick together, forming progressively larger bodies through a process called accretion. Small grains became pebbles, pebbles became boulders, boulders became planetesimals, and planetesimals collided to form the protoplanets. The four inner rocky planets, Mercury, Venus, Earth, and Mars, formed from material that could not easily become gas or ice at the temperatures close to the Sun. The outer solar system was cooler, allowing water, methane, and ammonia to freeze into solid ice grains. These ice-rich materials gave the outer planets access to far more solid material than was available to the inner planets, which is part of why Jupiter and Saturn are so much larger. Jupiter formed first among the giant planets, and its enormous gravity immediately began influencing everything around it. As Jupiter and Saturn continued to accumulate mass and their orbits evolved, a process that planetary scientists now believe was not the smooth, orderly, inward, then outward migration that early models suggested, but rather a chaotic, overlapping series of orbital resonances and gravitational interactions. They began scattering the smaller bodies in the outer solar system. The current leading model for the early evolution of the solar system, known as the Nice model, after the French city where it was developed in the early 2000s, proposes that Jupiter, Saturn, Uranus, and Neptune originally formed in a more compact configuration and then migrated outward over tens of millions of years as they scattered smaller bodies. This migration was violent. The giant planets plowed through the planetesimal disk like enormous gravitational bulldozers, flinging billions of icy bodies in every direction. Some of these ejected bodies gained enough energy from a close encounter with a giant planet to achieve escape velocity from the solar system entirely, leaving as interstellar wanderers. The two known interstellar objects detected in the solar system so far, the elongated object 1I/ALM, which passed through the inner solar system in 2017, and the comet 2I/Borisov, detected in 2019, may well be exactly this kind of material. Icy bodies ejected from another star's protoplanetary disk during its own chaotic early period. Now wandering through interstellar space, our own solar system would have contributed a similar population of expelled material to the galaxy. But not everything that the giant planets flung outward had enough energy to escape completely. A significant fraction of the ejected bodies had enough velocity to travel very far from the Sun, but not quite enough to break free of its gravity. They sailed outward to enormous distances, slowing as they went, and eventually stalled out at the very edge of the Sun's gravitational reach. These are the objects that now make up the Oort Cloud. Their initial trajectories, set by the slingshot interactions with Jupiter and Saturn, were mostly in the plane of the solar system. But over billions of years, two external forces gradually randomized those orbits into the spherical distribution. We observe today the first force is passing stars. The Milky Way contains roughly 300 billion stars, all orbiting the galactic center at various speeds and in various directions. Over the lifetime of the solar system, many thousands of stars have passed within a few light years of the Sun. Each passing star exerts a gravitational tug on the outer solar system, and the Oort Cloud is particularly susceptible to these perturbations because the Sun's grip on objects there is so weak. A star passing at a distance of several light years does not come close enough to directly capture or eject Oort Cloud objects, but it does perturb their orbits, shifting the shape and inclination of their paths by tiny amounts. Over millions and billions of years, these repeated small perturbations add up, gradually randomizing the orbital inclinations of Oort Cloud objects until they are distributed uniformly in all directions. The second force is more exotic, the gravitational tide of the Milky Way galaxy itself. The Milky Way is a disc-shaped galaxy with a mass of roughly 1 trillion solar masses, distributed across a region roughly 100,000 light-years in diameter. Like any extended mass distribution, it creates a tidal force, a differential gravitational pull across the extent of the solar system. The side of the Oort Cloud closer to the galactic plane is pulled slightly differently than the side farther from it. This differential pull, the galactic tide, slowly distorts and stretches the orbits of Oort Cloud objects, torquing them out of the plane of the planets and contributing to the spherical distribution. The galactic tide is estimated to be responsible for a substantial fraction of the long-period comets that enter the inner solar system. As the galactic tidal force slowly changes the shape of an Oort Cloud orbit over millions of years, it can eventually bring the orbit's closest approach point, the perihelion, into the inner solar system. The comet then begins a long inward fall, crossing the planetary system for the first time in billions of years. The balance between the Sun's weak gravity and the galactic tide in the Oort Cloud is not a static equilibrium. It fluctuates as the solar system oscillates through the galactic plane in its roughly 225 million year orbit around the galactic center. The solar system is not stationary relative to the galactic disk. It bobs up and down through the plane of the galaxy, roughly every 32 to 35 million years, alternately passing through regions of higher and lower stellar density. Some researchers have proposed that these oscillations correlate with periodic comet showers that might explain periodic patterns in the terrestrial impact record, though this hypothesis remains contested. What is not contested is the vulnerability of the Oort cloud. We have already identified one specific star whose future trajectory will take it directly through the outer Oort cloud. It is called Gliese 710, a red dwarf star currently located approximately 60 light-years from the Sun. Unlike most stars, which either recede from us or approach and then recede, Gliese 710 is on a trajectory that will bring it to a minimum distance from the Sun of approximately 13,000 astronomical units, well, inside the outer Oort cloud in approximately 1.5 million years. When Gliese 710 passes through the cloud, it will act like a hand stirring a jar of sand. Its gravity will scatter enormous numbers of Oort cloud objects out of their current stable orbits. Some will be thrown further out into the galaxy or ejected from the solar system entirely, but a large fraction will be scattered inward, their perihelion distances reduced until they enter the planetary system for the first time. The result, according to calculations published by astronomers Corin Baylor-Jones and Rainer Dremel, using data from the European Space Agency's Gaia spacecraft, will be a comet shower, an elevated flux of long-period comets entering the inner solar system that could last for several million years. Estimates of the magnitude of this shower vary, but some calculations suggest the rate of long-period comets entering the inner solar system could increase by a factor of several compared to the current background rate. This is not a theoretical concern. Stellar encounters of this kind are a regular feature of the solar system's history. It is estimated that over the past billion years, stars have passed within 1 light-year of the Sun at a rate of roughly 1 to 3 per million years, with encounters within 2 to 3 light-years occurring more frequently. Each of these close passes would have produced comet showers of varying intensities. Some of the large impact events in Earth's geological record may trace back to comet showers triggered by ancient stellar encounters with the Oort cloud. Understanding the Oort cloud, therefore, connects directly to understanding the history of bombardment. Events on Earth, including events that may have influenced the evolution of life. The large impactor responsible for the end Cretaceous mass extinction 66 million years ago was, for many years, assumed to be an asteroid from the inner solar system, but an alternative hypothesis proposed by Avi Loeb and Amir Siraj in 2021 suggests that a significant fraction of the largest craters on Earth, including Chicxulub, could have been caused by long-period comets from the Oort cloud, whose perihelion distances were reduced by Jupiter's gravity on a single pass through the inner solar system. This specific hypothesis remains under investigation, but the broader point that the Oort cloud is dynamically connected to the history of impact events on Earth is well established. All of this discussion of what the Oort cloud is, where it came from, and what it does rests on an unusual epistemic foundation. We have never actually seen it. Not a single confirmed Oort cloud object has ever been directly imaged. no telescope has ever resolved a specific rock or ice body confirmed to be orbiting in the main cloud. The Oort Cloud, despite being the dominant spatial feature of the solar system by volume, is entirely invisible to us. This seems surprising given the capabilities of modern astronomy. The Hubble Space Telescope can image galaxies billions of light-years away with extraordinary detail. Ground-based telescopes with adaptive optics can resolve features on the surfaces of large asteroids. The James Webb Space Telescope, launched in December of 2021 and operational since 2022, can detect the atmospheric composition of exoplanets orbiting distant stars. Why can none of these instruments see objects in our own solar system that lie, by cosmic standards, in our immediate vicinity? The answer is a combination of three physical problems that all work against detection simultaneously. The first is distance. Objects in the Oort Cloud, even at its inner edge, are thousands of astronomical units from the Sun. The intensity of sunlight falls off as the square of distance. At 2,000 astronomical units, the nearest point in the Oort Cloud, sunlight is 4 million times dimmer than it is at Earth's distance. At 50,000 astronomical units, mid-cloud sunlight is 2.5 billion times dimmer than at Earth. Several kilometers across would reflect only a tiny fraction of that already vanishingly faint illumination back toward any telescope looking for it. The second problem is temperature. Because these objects receive so little sunlight, they are extraordinarily cold. The surface temperature of an Oort Cloud object is estimated at somewhere between 4 and 12 degrees Kelvin above absolute zero, colder than anywhere in the observable solar system, and barely above the temperature of the cosmic microwave background, which is 2.7 degrees Kelvin. At these temperatures, thermal emission from the objects themselves is almost undetectable, even to infrared telescopes. The James Webb Space Telescope's mid-infrared instrument, MIRI, which can detect heat radiation from objects far too faint for optical instruments, would struggle to distinguish an Oort Cloud object's thermal signal from the cosmic background noise. The third problem is size. Most Oort Cloud objects are believed to be relatively small, a few kilometers to tens of kilometers across. Distinguishing a faint, cold, small object against the background of billions of stars and galaxies requires angular resolution that current instruments cannot achieve at Oort Cloud distances. An object 10 kilometers wide at a distance of 10,000 astronomical units would appear as an unresolved point source with a brightness far below the detection threshold of existing surveys. Current sky surveys, like the Legacy Survey of Space and Time, or LSST, operated by the Vera C. Rubin Observatory in Chile and scheduled to begin full survey operations in the mid-2020s, will scan the sky with unprecedented sensitivity and cadence. But even LSST, with its enormous 8.5-meter mirror and wide-field camera, is not expected to detect confirmed Oort Cloud objects in the main cloud. It may detect objects in the inner Oort Cloud transitioning toward the planetary system, or Sedna-like objects in the scattered disk that represent the transition population between the Kuiper Belt and the Oort Cloud, but the main cloud itself remains beyond reach. One intriguing, recent approach involves occultations. When a small solar system object passes in front of a distant star, It briefly blocks the star's light, an occultation event that lasts only milliseconds for small objects at great distances. High-speed photometric surveys monitoring millions of stars simultaneously can, in principle, detect these events as statistical signatures and use them to constrain the population of small bodies in the outer solar system. The Taiwanese American Occultation Survey, or TOS, and its successor, TAOS-2, have pursued this strategy for the Kuiper Belt population. Extending this technique to Oort Cloud distances would require even faster cameras observing even more stars, but it represents one of the few observational strategies that could eventually provide statistical constraints on the Oort Cloud population without requiring direct imaging for now. However, our understanding of the Oort Cloud rests almost entirely on the indirect evidence provided by comets, specifically the distribution and characteristics of long-period comets that fall into the inner solar system. The story of how that evidence was assembled and interpreted begins with two astronomers working independently decades apart. The first was Ernst Julius Pick, an Estonian astronomer of extraordinary range and productivity, who in 1932 proposed that a distant comet reservoir must exist to explain the continuous supply of comets entering the solar system despite the finite age of any given comet. Pick calculated that if comets originated from a disk-like region near the planets, they would have been depleted long ago by solar heating and gravitational ejection. A distant reservoir, insulated from these destructive processes by its remoteness, was logically necessary. Pick's 1932 paper attracted little attention at the time. He was ahead of his observational data, and without a specific mechanism to explain how the reservoir fed comets into the inner solar system, the proposal remained speculative. The definitive analysis came in 1950, when the Dutch astronomer Jan Hendrik Oort published a landmark paper examining 46 well-measured long-period comet orbits. Oort focused specifically on what astronomers call the original semi-major axis of each orbit, of the orbit's shape before it was altered by the gravitational influence of the planets during its most recent passage through the inner solar system. By working backward through these planetary perturbations, Oort could reconstruct how far each comet's orbit extended at its most distant point before it began falling inward. What he found was striking. The distribution of original semi-major axes showed a pronounced clustering at very large values, orbits that tended to tens of thousands of astronomical units. This is the mathematical signature of a reservoir at that distance. A comet falling from an orbit that extends to 50,000 astronomical units, perturbed by the galactic tide or a passing star until its perihelion falls within the inner solar system, would have exactly the characteristics Oort measured. But Oort also found something more revealing. He examined the inclinations and orientations of these comet orbits, the angle at which each comet's orbit was tilted relative to the plane of the planets, and the direction in the sky from which each comet appeared to come. The distribution was completely uniform. Comets arrived from all inclinations with equal probability and from all directions in the sky with essentially equal frequency. This isotropy was the key diagnostic. If the reservoir were a flat disk, even a large one, The comets it supplied would arrive preferentially in the plane of the solar system. They would have preferred inclinations near 0 degrees. The fact that comets arrive with equal probability at all inclinations, including from directly above and directly below the solar plane, demanded a reservoir with spherical symmetry. The reservoir had to surround the solar system completely. Hence, the Oort Cloud. Oort's paper has held up remarkably well over the following 75 years. Subsequent analyses, using much larger samples of well-measured comet orbits, have confirmed his basic picture, refined the estimates of the cloud's extent and population, and added the distinction between the inner Hills cloud and the outer spherical component. The total number of objects in the Oort cloud is estimated at somewhere between 100 billion and 2 trillion, with most of the mass concentrated in the inner region. The combined mass of the cloud is difficult to measure, but is estimated at perhaps 5 to 10 times the mass of Earth, distributed across an astronomical volume. One piece of evidence for the Oort cloud that has emerged in recent decades comes from the discovery of a class of objects in the outer solar system that seem to occupy the transition zone between the Kuiper Belt and the main cloud. The most famous of these is Sedna. Sedna was discovered on November 14, 2003 by Michael Brown, Chad Trujillo, and David Rabinowitz using the Samuel Oschin telescope at the Palomar Observatory in California. It is a large, reddish body, roughly 1,000 kilometers in diameter, large enough to be roughly spherical, placing it in the category of potential dwarf planets. What made Sedna immediately remarkable was its orbit. At its closest approach to the Sun, Sedna comes to within 76 astronomical units of the Sun. At its most distant, it recedes to approximately 937 astronomical units, well inside the nominal inner boundary of the Oort cloud but far beyond the Kuiper Belt. This orbit has no good explanation within the standard picture of the solar system. The Kuiper Belt extends to roughly 50 astronomical units. The inner Oort cloud begins at roughly 2,000. Sedna occupies an orbit in the gap between these two populations, a region that our current understanding of solar system formation does not easily populate. No known planet and no known mechanism operating today can easily produce Sedna's orbit. Several hypotheses have been proposed. One is that Sedna was scattered to its current orbit by a passing star during the early history of the solar system, when the Sun was still embedded in its birth cluster of young stars. Close stellar encounters during that epoch could have raised the perihelion distances of objects from the Kuiper Belt into Sedna-like orbits. Another hypothesis is that a distant, massive planet, sometimes called Planet 9 or Planet X, currently orbiting in the outer solar system, is gravitationally shepherding Sedna and similar objects into anomalous orbits. The Planet 9 hypothesis was proposed by Konstantinos Batygin and Michael Brown in 2016 to explain a statistical clustering in the orbital orientations of several extreme trans-Neptunian objects, with orbits that extend well beyond the Kuiper Belt. Their analysis suggested that a planet roughly 5 to 10 times the mass of Earth, orbiting at a distance of perhaps 400 to 800 astronomical units with a highly elongated orbit, could gravitationally hurt these objects into the clustering pattern observed. the hypothesis has neither been confirmed nor conclusively ruled out. Searches for Planet 9 using existing telescopes have found nothing, but the expected brightness of a planet at that distance is well below the sensitivity of current surveys. The Vericy-Rubin Observatory's Legacy Survey of Space and Time may be capable of detecting or ruling out a significant portion of the proposed parameter space, but results will take years to accumulate as the survey builds up coverage. Whether or not Planet 9 exists, Sedna and the handful of similarly extreme objects discovered since, including 2012 VP 113, nicknamed Biden, discovered in 2012 by Scott Shepard and Chad Trujillo, demonstrate that the outer solar system is not empty. Between the Kuiper Belt and the Oort Cloud, there is a population of objects in that intermediate zone whose formation and current dynamics are not fully explained by existing models. Brings us to the spacecraft that has traveled farther from Earth than any other human-made object, and what its journey actually tells us about the scope of the solar system. Voyager 1 was launched on September 5, 1977, from Cape Canaveral, Florida, carrying a suite of scientific instruments designed to study the outer planets and their environments. After flying past Jupiter in March of 1979 and Saturn in November of 1980, it continued on a trajectory that would take it out of the planetary system and eventually into interstellar space. New Horizons, launched in 2006, eventually surpassed Voyager 1 in the direction of Pluto, but will not surpass Voyager 1's distance from the Sun for many decades. As of 2025, Voyager 1 is approximately 162 astronomical units from the Sun, the most distant human artifact in existence. It is traveling at about 17 kilometers per second, which translates to roughly 60,000 kilometers per hour, or about 38,000 miles per hour. These numbers sound enormous by everyday standards. In the context of the solar system's actual scale, they are not. On September 12, 2013, 42 days before NASA made an official announcement, analysis of Voyager 1's plasma wave instrument data confirmed that the spacecraft had crossed the heliopause. The heliopause is the boundary where the solar wind, the continuous flow of charged particles emanating from the Sun, is no longer strong enough to push back the interstellar medium, the diffuse plasma and magnetic fields that permeate the space between stars. Beyond the heliopause, the solar wind's particles give way to the particles of the local interstellar medium, and the magnetic field lines shift in direction, becoming aligned with the broader galactic field, rather than the Sun's field. This boundary is often described as the edge of the solar system, and in a magnetic and particle physics sense, it is accurate. Inside the heliosphere, the bubble of solar influence. Outside is interstellar space, but the heliopause is not the same as the edge of the Sun's gravitational territory. Gravity has a much longer reach than the solar wind. The gravitational sphere of influence of the Sun, the region where the Sun's gravity dominates over the gravitational effects of neighboring stars and the galactic tide, extends to distances comparable to the Oort Cloud, where Voyager 1 crossed into interstellar space in 2013, sits at roughly 123 astronomical units. The inner edge of the Oort Cloud sits at 2,000 to 5,000 astronomical units. Voyager 1 has not come close to the Oort Cloud. It is not approaching the Oort Cloud in any meaningful near-term sense. At its current speed, and assuming no change in trajectory, it will reach the estimated inner edge of the Oort Cloud sometime in approximately 2,000 years. Perhaps closer to the 23rd or 24th century, if the inner boundary is at the lower end of the estimated range. The spacecraft will not reach the middle of the Oort Cloud for thousands of years, and will not emerge from the far side until roughly 30,000 years from now. The problem is that Voyager 1 will have long since gone silent by then. The spacecraft is powered by 3 radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium to 38 into electricity. Through the Seebeck effect, the generation of electrical current across a temperature gradient between the hot radioactive core and the cooler outer casing. Plutonium-238 has a half-life of 87.7 years, meaning that the amount of thermal energy it produces falls by half roughly every 88 years since launch. In 1977, approximately 48 years have passed as of 2025. Voyager 1's power output has fallen substantially from its original level of roughly 470 watts of thermal power at launch. By the early 2030s, NASA engineers estimate that there will no longer be enough electrical power to operate any of the remaining active scientific instruments. The last instruments will be shut down, and Voyager 1 will become a silent piece of metal drifting through the void. Its radio transmitter, finally dark after more than 5 decades of continuous operation. The spacecraft will continue its trajectory after going silent, maintaining its course through the outer solar system by the same gravitational dynamics that have guided it since Saturn. But it will have no means of transmitting data back to Earth, and no power for any instrument to collect it. Voyager 1 will drift through the empty space between the heliopause and the Oort Cloud, enter the cloud sometime in the middle of the current millennium, or later, traverse the cloud over the following 30,000 years, and eventually emerge on the other side, a human artifact wandering silently through interstellar space. Its last transmissions, a faint historical echo. This particular fact, that the fastest object humanity has ever successfully launched into interstellar space will take 30,000 years just to cross the threshold of our solar system's outer shell, is perhaps the single most important datum for understanding the engineering challenge of interstellar travel. 30,000 years is longer than the entire recorded history of human civilization. It is longer than the gap between the construction of the oldest known megalithic monuments and today. It is roughly the time since anatomically modern humans first arrived in Europe. The entire arc of agriculture, cities, writing, mathematics, philosophy, religion, science, industry, and digital technology has occurred within a span of time shorter than what Voyager 1 needs just to cross the Oort Cloud. And Voyager 1 is, by any measure, an extraordinary engineering achievement. It has been operating continuously for nearly 5 decades. Its instruments have directly measured the properties of the solar wind, the magnetospheres of Jupiter and Saturn, and now the local interstellar medium. It is humanity's best probe of the outer solar system, and it cannot even reach the Oort Cloud within a civilization's lifespan. The engineering barrier is not primarily about speed. It is about the rocket equation. The Tsiolkovsky rocket equation describes the fundamental constraint on any rocket-propelled vehicle. In simple terms, to accelerate a spacecraft, you must expel mass in the opposite direction. The fuel that provides this expelled mass is itself mass that must be carried and accelerated. This creates an exponential relationship between the speed you want to achieve and the amount of fuel required. To double your exhaust velocity, you do not double your fuel requirements, you square them. To increase your final speed by a factor of 10 relative to your exhaust velocity, the ratio of initial fuel mass to final payload mass must be raised to the power of roughly 10 divided by exhaust velocity. For chemical rockets, which burn conventional propellants like liquid hydrogen and liquid oxygen, the exhaust velocity is limited by thermodynamics to around 4 to 4.5 kilometers per second. To reach the speeds needed for an interstellar journey in any reasonable time frame, perhaps 1% of the speed of light, or 3,000 kilometers per second, which is still about 700 times Voyager 1 speed, the fuel mass required dwarfs the payload mass by factors that make practical spacecraft essentially impossible with chemical propulsion. The Oort Cloud makes this worse, not better, by removing the possibility of island hopping, using resources found along the route to supplement carried fuel. In the inner solar system, spacecraft could, in principle, refuel from asteroids, comets, or planetary moons encountered en route. But the Oort Cloud, despite containing trillions of icy objects, has those objects distributed across a volume so enormous that the density is effectively zero. The average distance between neighboring Oort Cloud objects is estimated at tens of millions of kilometers, comparable to the distance from Earth to Saturn. There are no convenient stopping points. Nuclear propulsion offers substantially better exhaust velocities than chemical rockets, potentially reaching 20 to 60 kilometers per second or more, depending on the design. Project Orion, an American design study conducted in the late 1950s, proposed propelling a spacecraft by detonating a series of nuclear bombs behind a pusher plate, potentially achieving exhaust velocities of 30 to 60 kilometers per second. A later concept, Project Daedalus, studied by the British Interplanetary Society in the 1970s, proposed a design using inertial confinement, fusion, compressing small pellets of deuterium and helium-3 with electron beams until they underwent nuclear fusion to achieve exhaust velocities of several thousand kilometers per second. Daedalus was designed to reach Barnard's star, a red dwarf about 6 light-years away, in approximately 50 years. The challenge with fusion propulsion is that inertial confinement. Fusion has not yet been demonstrated in a form that produces more energy than it consumes. Though the National Ignition Facility at Lawrence Livermore National Laboratory achieved fusion ignition net energy gain from the fuel capsule in December of 2022, a milestone after decades of effort, practical fusion propulsion remains decades away at minimum and faces engineering challenges. Beyond just the physics of the reaction, the most widely discussed alternative for near-term interstellar exploration is laser-driven light sail propulsion. The Breakthrough Starshot Initiative, announced in 2016 and backed by a $100 million research commitment, proposes accelerating a gram-scale spacecraft, essentially a microchip with a reflective sail, to approximately 20% of the speed of light, using a powerful ground-based laser array, directing a focused beam at the sail. At 20% of light speed, such a probe could reach Proxima Centauri in approximately 20 years. A similar probe aimed at the Oort Cloud could traverse it in a matter of months rather than millennia. The engineering challenges of breakthrough Starshot are substantial. The laser array would need to deliver a focused beam of approximately 100 gigawatts to the sail, more power than most countries generate for a few minutes of acceleration. The sail itself must be extraordinarily thin and highly reflective to achieve the required thrust-to-mass ratio while surviving the intensity of the beam. The spacecraft must function and transmit data using essentially no mass budget. None of these challenges have been solved, but they are considered engineering problems rather than fundamental physics violations. What no near-term technology can solve is the problem of sending humans. A laser sail probe of gram-scale mass is physically possible, at least in principle. A human crewed vessel capable of sustaining life across the decades or centuries of even an optimistic interstellar journey, carrying enough shielding against cosmic rays and micrometeorites, enough propellant or collected fuel. This is not a problem that current or foreseeable technology addresses. The Oort Cloud is a desert, and crossing a desert requires carrying everything. The contrast between the conceptual familiarity of leaving the solar system and the physical reality of what that requires is stark. In popular culture, spacecraft routinely zip between star systems. In physical reality, the fastest object humanity has ever launched will require 30,000 years to cross the solar system's outer boundary, will go silent before it gets there, and will carry no human aboard. The Oort Cloud is not a modest obstacle. It is a boundary defined by the laws of physics as they apply to the technology. Available to a civilization roughly as advanced as ours, there is something worth sitting with in that gap. Every human who has ever lived has existed inside this shell. Every spacecraft ever launched has, at best, barely scratched the inner surface of it. Every astronomical observation ever made has been conducted from inside this bubble. We have no direct sample of Oort Cloud material. We have no image of a single confirmed Oort Cloud object. We have never sent a probe that will reach the cloud while still functioning. The shell that defines the outer boundary of our solar system is, for all practical purposes, unreachable with anything we can currently build, and yet it shapes our world in ways that are concrete and measurable. Long-period comets, which have caused the most dramatic impacts in the history of the inner solar system, come from there. The rhythm of comet showers that may correlate with mass extinction events on Earth traces back to the dynamics of the cloud. The chemistry of the early solar system, preserved in the ice of Oort Cloud objects for 4.5 billion years, is readable, if incompletely, in the comets that occasionally fall inward. The possibility of a comet shower in 1.5 million years, triggered by the approach of Gliese 710, is a direct consequence of the cloud's existence and vulnerability. The Oort Cloud is simultaneously the most distant and one of the most practically relevant structures in the solar system. It is the archive of our origins, the reservoir of our most energetically significant visitors. and the barrier that defines the practical limits of our reach. It is made of the same material as the earliest solar system, pristine ice from 4.5 billion years ago, stored at temperatures barely distinguishable from the coldest environment. The universe naturally produces to reach it. To send a functioning probe through it and out the other side would require either a century of patient waiting while fusion, propulsion, or laser drive technology matures, or a timescale of geological patience measured in tens of thousands of years with chemical technology. Neither option fits any planning horizon that existing human institutions can meaningfully address. What astronomers are focused on in the near term is indirect characterization, using the comets that fall into the inner solar system as messengers from the cloud, and using occultation surveys and statistical methods to constrain the cloud's population without ever directly observing it. The Vera-C-Rubin Observatory, when it reaches full operations, will detect thousands of new comets per year, including more long-period comets than have ever been systematically studied. Each of these comets is a sample from the cloud, a frozen fragment carrying chemical information about the conditions. In the early solar system 4.5 billion years ago, the discovery of interstellar objects, bodies passing through the solar system on hyperbolic trajectories that can only originate from outside our star system, adds another dimension to this picture. Oumuamua in 2017 and Borisov in 2019 were the first detected examples of material from other stellar systems passing through our solar system. Statistical analysis suggests that the solar system should be transited by several interstellar objects per year that are large enough to detect, and that the Oort Cloud itself likely captures a small fraction of the interstellar objects that pass through it. Some of these may be incorporated into the cloud over geological timescales, carrying material from other stellar systems into our own. This means the Oort Cloud may not be purely solar in origin. A small fraction of its objects might be interstellar in origin, captured from the material ejected by other star systems during their own chaotic early periods, or contributed cluster that surrounded the young sun. The sun is believed to have formed in a stellar birth cluster of hundreds or thousands of stars, and during the first few million years of the solar system's existence, while the sun was still embedded in that cluster, the gravitational cross-sections for capture were much larger than they are today. The Oort Cloud may therefore contain a small admixture of material from neighboring stars in our birth cluster. What does it mean to stand at our current position and look outward at a structure of this scale, this antiquity, and this inaccessibility? The Oort Cloud is the true scale of our home, not the solar system as most people picture it, a compact family of planets orbiting a star, but a sphere, hollow at center, filled with the primordial debris of our origin, extending halfway to the next star, sensitive to the gravitational tides of the entire galaxy, and as inaccessible to us in practical terms as the surface of a neutron star. It defines where we actually live more accurately than any planetary map does. There is a distinction between living inside something and being aware of it. Every human who has ever existed, every civilization that has risen and fallen, every artifact ever created has been embedded within this structure. It has always been there, shaping the flux of comets that occasionally alter planetary histories. But it took the patience of Jan Oort in 1950, sitting in a post-Oort Dutch university, computing the trajectories of comets by hand, detecting a pattern in the distribution of orbits that implied a structure no telescope could see, to establish that it exists at all. The Oort Cloud is a structure we know primarily through its consequences and through the logical necessity of its existence. It is a reminder that the solar system is not what it appears on the maps, that most of the territory of our home has never been visited, and that the barrier between the solar system and interstellar space is not a matter of simple distance. It is a matter of physics, thermodynamics, and the rocket equation applied to a desert several hundred astronomical units wide at minimum. If you find this kind of evidence-based exploration of the structures that define where we live worth staying with, subscribing means you see the next piece of this puzzle as it comes together. The Oort Cloud is not a distant abstraction. It is the outer wall of our home. It is older than Earth, colder than any temperature we experience at the surface of our planet, and so vast that our fastest spacecraft cannot cross it in any time frame that maps onto human planning. Its icy objects carry the chemical fingerprints of the early solar system. Its dynamics are entangled with the motion of stars around the galaxy. Its future perturbations will eventually send showers of comets inward, as they have done repeatedly in the past. We have never seen it directly. We know it exists because the comets it periodically delivers to the inner solar system could not come from anywhere else. We know its approximate scale and population from the mathematical analysis of 400-odd measured comet orbits. We know it is vulnerable to perturbation from stars that have already passed and from stars like Gliese 710 that have not yet arrived. Scientists are now working to constrain its properties further using multiple converging approaches. Wide-field sky surveys will discover more long-period comets, building a larger statistical sample for orbital analysis. Occultation monitoring programs will attempt to detect the shadow of small outer solar system bodies crossing distant stars. The search for more Sedna-like objects in the transition zone between the Kuiper Belt and the Oort Cloud will illuminate the population of bodies in the inner cloud region. Infrared space telescopes operating at unprecedented sensitivity may eventually detect the thermal emission from Oort Cloud objects if instrument technology continues to advance. And beyond the instrumentation, the theoretical understanding of how the cloud formed, how the galactic tide maintains its spherical shape, and how stellar perturbations periodically flood the inner solar system with comets, continues to deepen with better computational models and better constraints from observational data, what science does not yet know about. The Oort Cloud is substantial. The total mass of the cloud remains uncertain by more than an order of magnitude. The transition between the disc-shaped inner Hills cloud and the spherical outer Oort Cloud is not well characterized. The fraction of Oort Cloud objects that are truly spherical bodies versus elongated fragments is unknown. The chemical diversity of the cloud, whether all long-period comets resemble each other, or whether there is significant compositional variation, is only beginning to be explored as larger samples of comets are analyzed. Most fundamentally, we have never confirmed the existence of a single Oort Cloud object directly. Every specific claim about the cloud is inferred from the properties of comets that have long since entered the inner solar system and been modified by solar heating and planetary perturbations. The source population itself remains invisible. That invisibility is not a problem unique to the Oort cloud in the history of science. Dark matter, which constitutes roughly 27% of the total energy density of the universe, has also never been directly detected in a laboratory. Its existence is inferred from gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the cosmos. Exoplanets were, until the 1990s, entirely inferred objects. Their existence was logically necessary given the properties of stellar systems, but none had been directly imaged. The Oort cloud sits in that tradition of objects whose existence is established by rigorous, indirect evidence to a degree that leaves essentially no scientific doubt, but whose direct confirmation awaits technology that does not yet exist. It is, in that sense, one of the most securely established invisible structures in astronomy, a shell of frozen history wrapped around everything we have ever called home. To appreciate why the Oort cloud matters beyond its role as a distant comet reservoir, it is worth examining in more detail what comets themselves have taught us about the early solar system and, by extension, about the conditions that made life on Earth possible. Comets are often called the pristine remnants of the early solar system, a phrase that is accurate but requires unpacking. When the solar system was forming 4.5 billion years ago, the material in the outer regions, beyond the frost line, the distance from the sun where temperatures were low enough for water to freeze, was predominantly water ice laced with frozen carbon-bearing compounds and silicate dust grains. These materials coalesced into small bodies called planetesimals, the building blocks from which the giant planets eventually formed. The key distinction between a comet and an asteroid is primarily compositional. Asteroids, formed in the inner solar system where it was too warm for volatiles to condense, are primarily rocky and metallic. Comets, formed in the cold outer solar system, are ice-rich bodies that carry a substantial inventory of frozen water, carbon dioxide, carbon monoxide, methane, ammonia, and various complex organic molecules. When a comet falls into the inner solar system and is heated by the sun, its ices sublimate, converting directly from solid to gas without passing through a liquid phase. Because the pressure at a comet's surface is too low for liquid water to be stable, this sublimation releases not just gas, but also the dust grains and complex molecules mixed into the ice matrix. The resulting cloud of gas and dust around the nucleus is called the coma, and the twin tails, the dust tail pushed away from the sun by radiation pressure, and the ion tail pushed away by the solar wind, make comets among the most visually striking phenomena in the night sky. The coma of a comet is a chemical snapshot of its nucleus, which is itself a chemical snapshot of the conditions in the outer solar system 4.5 billion years ago. Analyzing the coma with spectroscopic instruments allows astronomers to determine what molecules are present and in what proportions. This analysis has consistently revealed comets to be extraordinary chemistry labs, containing not just simple molecules like water and carbon dioxide, but complex organic compounds, including formaldehyde. methanol, formic acid, acid acetaldehyde, acetic acid, and glycolaldehyde, a simple sugar molecule. The detection of glycine, the simplest amino acid, one of the 20 amino acids that make up proteins in living organisms, in the coma of Comet Wild 2 by NASA's Stardust mission, which returned cometary material to Earth in 2006, and subsequently in Comet 67P by the Rosetta mission, confirmed that the chemical building blocks of biology are present in comets. This is relevant to a long-standing question in the study of life's origins. Where did the organic molecules from which life assembled itself come from? Earth, during its early history, was a violent place. The first 500 million years of the planet's existence, a period geologists call the Hadean, from the Greek word for underworld, were characterized by continuous large impacts from the debris left over after the planets formed. The late heavy bombardment, an era of elevated impact flux believed to have peaked roughly 3.9 billion years ago, showered Earth and the other inner planets with asteroids and comets. This era may have been triggered by a gravitational reorganization of the giant planets, the kind of migration captured in the NICE model that destabilized the Kuiper Belt and the Oort Cloud, sending a pulse of comets into the inner solar system. Comets impacting the early Earth delivered water, complex organic molecules, and potentially amino acids directly to the planet's surface. Some researchers argue that a significant fraction of Earth's current ocean water may have been delivered by comets during the late heavy bombardment. The ratio of deuterium, a heavy isotope of hydrogen, to ordinary hydrogen in ocean water can be compared to the same ratio measured in comets to test this hypothesis. Results so far have been mixed. Some comets match Earth's water isotope ratio well, others do not. Asteroids from the outer asteroid belt also match reasonably well, suggesting Earth's water was probably delivered by a mixture of sources, rather than purely by comets. But the delivery of organic molecules is less isotopically constrained and may have been dominated by comets. The complex organic chemistry of comets, combined with the energy available at impact sites, where shockwave heating and liquid water are both present, could potentially catalyze the formation of more complex molecules from simpler precursors. Whether this cometary delivery played a significant role in the origin of life, or whether life's building blocks, assembled primarily from terrestrial chemistry, remains one of the most contested questions in astrobiology. What is clear is that the icy material locked in the Oort Cloud, the same material that occasionally falls into the inner solar system as long-period comets, is chemically connected to the story of life on Earth. The Oort Cloud is not just a gravitational curiosity. It is the largest repository of the chemical raw material that influenced Earth's early chemistry and possibly contributed to the conditions that made life possible. The history of comet observation provides context for how our understanding of these objects has evolved. For most of human history, comets were regarded as portents, ominous signs in the heavens that presaged the fall of kings, plagues, or military defeats. The unpredictability of their appearance, their dramatic visual impact, and the fact that they followed no apparent pattern in the sky made them natural candidates for supernatural interpretation. The first scientific analysis of a comet's motion came from Edmund Halley, who recognized in 1705 that the comets observed in 1682, 1607, and 1531 were all the same object, returning periodically. By applying Newton's newly published laws of gravity to the orbital data, Halley calculated that the comet moved in an elongated ellipse with a period of approximately 75 to 76 years, and predicted it would return around 1758. It did, becoming the first comet to have its return successfully predicted and cementing Halley's name to the most famous periodic comet in human knowledge. Halley's Comet, designated officially as 1P/Halley, is a short-period comet originating from the Kuiper Belt, or possibly the scattered disk rather than the Oort Cloud. Its 75-year orbital period has allowed historians to trace its appearances back through ancient records. It was observed by Chinese astronomers as early as 240 BCE and appears in the Bayeux Tapestry depicting the Norman conquest of England in 1066 CE, when its appearance was likely interpreted as an omen for Harold II, who was defeated at the Battle of Hastings that same year. Short-period comets, like Halley's, with orbits of less than 200 years, are well studied and predictable. They are the comets around which missions have been designed and executed. The European Space Agency's Giotto mission flew within 600 kilometers of Halley's nucleus in March of 1986, returning the first close-up images of a comet nucleus, a dark, irregularly shaped body roughly 15 by 8 kilometers in size, with bright jets of gas and dust erupting from active regions where sunlight directly heated the surface. Long-period comets from the Oort Cloud are more scientifically interesting in terms of compositional purity, but much harder to study. They arrive on hyperbolic or near parabolic orbits, with orbital periods of thousands to millions of years, appearing with little warning and spending only weeks to months in the inner solar system before receding back toward the outer solar system. Designing a rendezvous mission to a long-period comet is technically far more challenging than designing one to a short-period comet, because the hyperbolic approach velocity would require an enormous expenditure of fuel to match. The most spectacular long-period comets in modern observation history include Comet West in one of the brightest comets of the 20th century, Comet Hyakutake in 1996, which passed within 15 million kilometers of Earth, and Comet Hale-Bopp in 1997, which was visible to the naked eye for an extraordinary 18 months and is estimated to have been observed by more people than any other comet in history. Its nucleus is estimated at approximately 60 kilometers in diameter, making it one of the largest comets ever confirmed to have entered the inner solar system. Hale-Bopp's next return is calculated to be approximately 4,380 years from now. The comet that astronomers and planetary scientists most eagerly anticipated in recent decades was Comet Isoin, discovered in September 2012 by Russian astronomers Vitaly Nevsky and Artyom Novichenok using the International Scientific Optical Network telescope in Russia. Isoin was a dynamically new comet, one making its first passage through the inner solar system. arriving from the Oort Cloud with an orbital period estimated at millions of years. It was expected to pass within approximately 1.16 million kilometers of the Sun's surface on November 2013, raising hopes that it could become one of the brightest comets in decades. Dynamically new comets making their first inner solar system passage are of particular scientific interest because they are thought to be the most compositionally pristine. They have never been heated by the sun before, so their volatile content represents the original chemistry of the outer solar system rather than the depleted composition of a comet that has already boiled off its most volatile ices in previous passages. Ison was indeed exceptionally active at large distances from the Sun, suggesting a high volatile content. Unfortunately, Ison did not survive its close approach to the Sun. The intense tidal forces and heating at perihelion broke the nucleus apart. By the time it emerged from perihelion, it was a rapidly dispersing cloud of debris rather than an intact nucleus, and it faded dramatically within days. The disappointment of comet Ison disintegration highlighted how physically fragile cometary nuclei can be under extreme conditions. The very volatility that makes new comets compositionally interesting also makes them susceptible to thermal and tidal disruption. The detection in late 2023 of comet Suchan-Chenatlis, officially designated C 2023-A3, marked another occasion of significant public interest. This long-period comet, with an estimated period of around 80,000 years, reached naked eye visibility in September and October of 2020, becoming one of the brighter comets visible from the northern hemisphere in several years and providing an opportunity to study a relatively pristine Oort Cloud visitor at relatively short notice. Each of these events, each visit by a long-period comet, is in some sense a message from the Oort Cloud, a frozen sample of the early solar system briefly exposed to the light of the sun, releasing its chemistry in a display of gas and dust that we can analyze spectroscopically. Understanding the diversity of compositions across different long-period comets will eventually paint a picture of the compositional structure of the outer solar system at the time of formation. Testing current models of how and where different icy materials condensed and accreted beyond comets, the Oort Cloud connects to a broader set of questions about the relationship between the solar system and the galaxy. The Sun is not a static object in galactic space. It orbits the center of the Milky Way at approximately 220 kilometers per second, completing one full galactic orbit roughly every 225 to 250 million years. This period is sometimes called the cosmic year or galactic year, and roughly 18 to 20 cosmic years have elapsed since the formation of the solar system 4.5 billion years ago. During each cosmic year, the solar system's position in the galaxy changes substantially. It moves through regions of varying stellar density, through the spiral arms of the galaxy with their elevated concentrations of molecular gas clouds and young stars, and through the disk of the Milky Way while oscillating above and below the galactic plane. Each of these environmental changes affects the Oort Cloud in different ways. When the solar system passes through a spiral arm, the increased density of stars and molecular clouds enhances the rate of gravitational perturbations. more stellar encounters occur per unit time, and the gravitational tides from dense molecular clouds add to the galactic tide in disturbing Oort Cloud orbits. Some researchers have proposed that the solar system's passages through spiral arms correlate with periods of elevated comet flux and, therefore, with periods of elevated impact rates on Earth. This produces identifiable signals in the geological record, such as clusters of large impact craters or pulses of mass extinctions, is debated. But the basic physics of the connection is straightforward. The solar system's oscillation through the galactic plane has a more regular periodicity. As the Sun moves above the plane, the gravitational pull of the mass concentrated in the plane draws it back down. It overshoots, passes through the plane, rises above the other side, and then falls back again. The full oscillation takes approximately 62 to 64 million years, roughly the same timescale as the period between several major mass extinctions in Earth's fossil record. This coincidence prompted the physicist Richard Muller and the astronomer Walter Alvarez, among others, to propose that galactic plane oscillations might cause periodic mass extinctions through comet showers. The hypothesis remains controversial. The statistical evidence for strict periodicity in mass extinctions is debated, and alternative mechanisms, including non-periodic comet showers from passing stars and purely internal geological processes, can explain many of the same patterns. But the basic connection between galactic dynamics, Oort cloud perturbation, and the flux of comets into the inner solar system is physically well grounded. And understanding the long-term history of this connection is an active area of research. What this broader perspective reveals is that the Oort cloud is not just a relic of the early solar system's formation. It is a dynamic interface between the solar system and the galaxy. It is sensitive to the gravitational environment of the galaxy, both locally through individual stellar encounters and broadly through the galactic tide. Changes in that environment, whether from the solar system's position in the galactic disk or from the approach of individual stars, propagate through the cloud and eventually manifest as changes in the flux of comets entering the inner solar system, the Earth. Sitting at the center of this nested set of gravitational influences is not isolated from the galactic environment. The thick shell of ice and frozen gas that constitutes the Oort cloud serves as a gravitational antenna for the galaxy's structure, converting distant gravitational influences into occasional showers of icy bodies that cross the inner solar system and rarely, but consequentially, strike the terrestrial planets. The history of life on Earth is not just a story about biology and chemistry. It is also, in part, a story about the gravitational dynamics of a star system moving through a galaxy. Looking further into the future of Oort cloud science, the coming decades will bring substantially improved observational capabilities. The Vera C. Rubin Observatory's legacy survey of space and time will survey the entire southern sky every few nights for 10 years with a 3.2 billion pixel camera and an 8.4-meter mirror, detecting moving objects too faint for any previous survey. By the end of its planned survey period, it is expected to have discovered more solar system objects, asteroids, trans-Neptunian objects, comets, than all previous surveys combined. The improved statistical sample of long-period comet orbits this produces will allow more precise mapping of the Oort Cloud structure, particularly the boundary region between the inner Hills cloud and the outer spherical component. The Nancy Grace Roman Space Telescope, NASA's next flagship space observatory scheduled for launch in the mid-2020s, will complement ground-based surveys with wide-field infrared observations that extend to fainter magnitudes and shorter wavelengths than ground-based instruments can achieve. It may detect the thermal emission from scattered disk objects and possibly constrain the population of inner Oort cloud objects at the extreme limits of current sensitivity in situ exploration. Sending a spacecraft to actually visit the Oort cloud or even a single Oort cloud object is a dream that requires technology not yet in hand but not beyond imagination. A spacecraft powered by nuclear electric propulsion, using a nuclear reactor to generate electricity that drives an ion engine, could reach substantially higher velocities than chemical rockets allow over multi-year acceleration periods, an ambitious concept studied by NASA in the early 2000s, called the Interstellar Precursor Mission, envisioned a spacecraft reaching 200 astronomical units within 50 years using a combination of a nuclear electric drive and a solar gravity assist, swinging close to the Sun to gain an additional velocity boost from the intense solar radiation pressure on a large reflective sail dot at 200 astronomical units. Such a mission would still be far short of the Oort cloud's inner edge, but it would reach the boundary region that Voyager 1 is currently transiting, beyond the heliopause and in the undisturbed interstellar medium, with functioning instruments rather than the dying battery of Voyager. The scientific return from measuring the properties of the local interstellar medium at 200 astronomical units with modern instruments would be substantial. A more ambitious mission targeting the inner Oort cloud at 2,000 or more astronomical units is conceptually possible with advanced nuclear propulsion, but would require decades of flight time and an international long-term commitment to maintaining and communicating with a spacecraft across distances that make even simple data transmission a technical challenge. The communication delay at 2,000 astronomical units would be approximately 11.5 days, each one-way signal transit taking nearly 2 weeks. By 10,000 astronomical units, the delay reaches 57 days each way. These delays are not insurmountable for a robotic mission. They are simply constraints that require mission designs that allow the spacecraft to operate autonomously for extended periods and that require scientists to plan observations and commands on schedules measured in months rather than hours. Interplanetary missions already operate under similar constraints, though less extreme. A mission to the Oort cloud would push these operational patterns to their limits. The most important question such a mission might answer is the simplest to state and the hardest to address from Earth. What do Oort cloud objects actually look like? We know their orbits, inferred from the comets they supply. We know their approximate size distribution, inferred from statistical models. We know their rough chemistry, inferred from comets that have already been partially heated and modified during their fall into the inner solar system. But we have never seen an Oort cloud object in its original, unmodified state, a pristine, frozen body orbiting in the deep cold with no solar heating no coma, no tail, preserving the composition it has held since the solar system formed, the nucleus of a long-period comet. By the time it becomes detectable as it approaches the inner solar system, has already been altered. The outer layers have begun to sublimate. Active jets have modified the surface. The most volatile ices have already been lost. The pristine nucleus of an Oort cloud object, unheated, would be a more direct window into the early solar system than any comet we have yet studied. A close flyby, or, far more ambitiously, a rendezvous and sample return mission to an Oort cloud object, would represent the most direct possible investigation of the cloud and its contents. The technical challenges are daunting. An Oort cloud object's orbit carries it at extremely low velocities relative to the Sun at those vast distances. The orbital velocities are tiny fractions of a meter per second. A spacecraft approaching the target from the inner solar system would need to dramatically reduce its own velocity to match the target's orbit, requiring a fuel mass that only advanced propulsion systems can deliver. Such a mission is not planned and not currently feasible. It represents the kind of long-term aspiration that motivates the development of new technologies: nuclear propulsion, laser drive systems, solar sails, without being achievable with any technology currently mature enough to fly. But the aspiration is scientifically justified. The Oort cloud contains the most pristine preserved material from the formation of the solar system, and reaching it directly would allow the kind of detailed compositional analysis that remote spectroscopy cannot approach for the foreseeable future. Our knowledge of the Oort cloud will continue to grow through indirect means, through the comets it sends to us, through the dynamical signatures it leaves in the distribution of trans-Neptunian objects, through the occasional interstellar visitor that might originate from another star's equivalent reservoir, and through the improving statistical and computational models that translate these indirect measurements into estimates of the cloud's properties. This is science at its most patient, building knowledge slowly, through inference and calculation and comparison, about something that cannot be directly seen or touched or sampled, because the distance is simply too great and the objects are simply too cold and too dark for any current instrument. It is a reminder that science does not always require the ability to go to a place or hold a sample in a laboratory. Sometimes it requires only the careful analysis of evidence that arrives from afar, and the willingness to follow a chain of reasoning wherever it leads, even to structures that exist beyond the reach of any telescope and will remain beyond the reach of any spacecraft for thousands of years. The Oort cloud is out there. Its trillions of frozen objects have been waiting in the dark for 4.5 billion years. The Sun, from that distance, is just a point of light, the brightest star in an otherwise ordinary-looking sky, indistinguishable as our star to any observer who did not know which one to look for. The galaxy stretches overhead in all its vastness. The nearest neighboring stars are still hundreds of millions of times further than the comets are from each other. It is the most remote territory we can reasonably claim as our own. It is older than any geology on Earth. It holds the chemistry of our origins in a cold so profound that the chemistry has barely changed since the Sun first ignited, and it defines, more precisely than anything else, the actual scale of the place we call home, Jan Oort, working in Leiden in 1950 without computers, without space telescopes, without the accumulated exoplanet data and galactic mapping surveys that now inform our picture of stellar environments, deduced the existence of a spherical shell of frozen bodies, extending nearly halfway to the next star from 46 well-measured comet orbits. He could not see the cloud. He could not visit it. He could not sample it. He could only read the mathematical signature it left in the trajectories of the comets it occasionally sent inward. That act of inference, building a confident scientific claim about a vast, invisible, unreachable structure purely from the patterns left in the data that reached him, is as clear an example of the scientific method working as intended as the history of astronomy provides. The cloud bears his name not because he built a telescope large enough to see it, but because he was patient and careful enough to understand what the evidence was saying. 75 years later, every major observation conducted since has confirmed and refined his picture. The cloud is there. It is real. It is older than Earth, and it is still waiting 4.5 billion years after its formation for us to find a way to reach it. The next steps: better surveys, more comets measured, sharper orbital statistics, improved dynamical models, and eventually technology capable of sending an instrument beyond the heliopause with functioning sensors will continue filling in the picture. Each long-period comet that sweeps through the inner solar system is another data point, another chemical message from the deep freeze, another constrained orbit that narrows the statistical description of the cloud it came from. What will not change for a very long time is the essential character of our relationship to the Oort cloud. We live inside it. We know it primarily through what it sends us, and the distance between us and it is, by any measure available to current technology, essentially infinite in practical terms. The solar system does not end at Neptune. It barely begins there. And the Oort cloud, the true edge of our home, remains exactly where it has always been, surrounding us in every direction, invisible, ancient, and silent. If this kind of deep, evidence-based look at the structures that shape our place in the universe is something you want to keep seeing, subscribing means you will be there for the next one. The science of the outer solar system is moving faster than it ever has, driven by new surveys, new instruments, and new missions. The picture will sharpen, but the Oort cloud itself, 4.5 billion years old, cold beyond measure, and unreachable within any human timescale we can honestly plan around, will remain one of the most extraordinary facts about the world we live in, that our home is not a small planetary system, but a vast, frozen sphere extending to the edge of another star's territory, and that we have figured this out without ever seeing a single piece of it directly.